So as I said that all of your slides are on our Brightspace course. They are under table of contents, lecture slides, and that's where your modules are. Under these modules, I will also post the recordings of the lectures that we are doing. Okay. So to begin with, organic chemistry is what? Organic chemistry is considered as the chemistry of carbon and hydrogen bonds. Are you all able to see what I'm writing? Okay, I will try and write a little bit bigger also, but you will have to remind me if you want me to write a little bit bigger. Okay, good. Thank you for responding. And so the first thing that you all need to remember is your periodic table. If you look at the periodic table, there is borane, carbon, nitrogen, oxygen, fluorine, and then argon. Now, why is the periodic table very important for all of us? It will be important because, oh, neon, not argon. As you see here, you must know how to read the periodic table so you can figure out the valence electrons of all of these atoms. So who can tell me how many valence electrons are in carbon? 4. And I forgot. Very good. Very good. So carbon has 4 valence electrons. How many nitrogen has?
5.
Mm-hmm. How many oxygen has?
6.
7. And then this has the complete octet. Neon has the complete octet. So this is the first piece of information that your periodic table is going to give you. What is the next piece of information? How many bonds this atom can have? Let's start from neon. It has 8 valence electrons. Its octet is complete. How many more atoms can this neon bond with?
Nothing.
0. Very good. Fluorine or all the halogens have 7. How many more bonds fluorine can make?
1.
Only 1. Okay. Is this clear to everybody, or anyone has any questions on this? Okay, let me call out somebody's name. Kiera Weston. Is that how you call your name, Kiera?
Yes, ma'am.
Okay, hello, Kiera. Can you tell me, if oxygen has 6 valence electrons, how many more bonds can oxygen make?
2.
Very good. Very good, Kiera. Thank you.
You're welcome.
Let's see. Nadia Williams.
Yes.
Is that how you say your name? Please let me know if you, if I'm not pronouncing your name correctly. Okay, so
Nadia. Yeah, that was right.
Okay, thank you, Nadia. So with 5 valence electrons, how many bonds can nitrogen make?
3.
Very good. Thank you, Nadia. And who wants to give a shout out of how many bonds a carbon can make?
4.
4.
4, very good. Now, these are very important pieces of information that all of you need to understand. Always remember, carbon cannot make more than 4 bonds. Nitrogen, oxygen can sometimes make 4 and 3 bonds, sometimes. But carbon will never do that. Never, ever 5 bonds. This is one of the basic things that all of you need to remember. Now, when carbon was discovered, it was also discovered that it is a very special atom. It does not behave as expected. And that is why carbon makes the backbone of all the life form that we know of. So whenever we talk about organic chemistry, we are actually talking about long chains of carbon hydrogen bonds. Well, I forgot one of the atoms here. Hydrogen only has one s orbital. It only has one electron. How many valence electrons are there? Only one. How many bonds hydrogen can make? Only
1.
one. Very good. So these are the things that you will have to remember, especially for the beginning of the course, because you will have to draw several structures. And we'll talk about that when we come there. So these chains of carbon-carbons and carbon-hydrogen bonds, this is what has led to form the organic materials. In the very beginning, only nature was allowed, nature could make organic materials. But eventually in 1820s, several discoveries were made, and they are not important for our course, just for the knowledge that they were the first time that organic material was synthesized in lab. So it was a big deal. Now, these carbon chains can be organized into different manners. What I have shown you is known as a linear form. Let's count how many carbons did I make. I have 5 carbons. I can arrange these 5 carbons in this manner also. I can arrange my 5 carbons in this manner also. These are known as the branched forms. Same 5 carbons. And I'm just numbering them randomly. So this different arrangement of atoms that carbon chains can assume led to different properties. And we will read in module 4 how these chain or linear or branched forms are differing in melting points, boiling points, and things like that. But in the beginning, I just want you to remember that carbon makes 4 bonds. How many bonds am I showing you here for carbon 1? 1, 2, 3. You will always assume that if no other element is shown, the hidden atom will always be a hydrogen. Okay, so for example here, how many bonds am I showing with carbon right now? Only 1, because I know the rest of the 3 are going to be hydrogens. Who does not understand what I just said? Okay, do you want me to call out your name just like that? Masha Ren. Is that how you say your name? Majsha?
Masia.
Maja? I'm sorry, could you repeat that?
Masia.
Meja. Okay. Meja Ren. Is that how you say it, or am I twisting it?
That's right.
Okay, Meja. Meja, how many bonds this carbon has?
4.
How many bonds this carbon should have?
3.
So it has this 1 bond, and then the other 3 will be hydrogens. Why? Because a carbon needs to make its 4 bonds. 1, 2, 3, 4. Does that make sense?
Yes.
Misha? Okay. Anyone else has a question? Why am I assigning hydrogens like this? Okay, Armani, Pace, are you good? I mean, I don't want to call out everybody's name, but I just want to make sure that every one of you understand.
Yes, I understand.
Okay, very good. Now, the next thing that these carbon atoms bonding to other elements give rise to are known as chemical bonds. Now, chemical bonds are nothing but when atoms combine of two valence shells so that they can get atomic, a noble gas configuration. Okay? So chemical bonds can be of variety of kinds. The most popular ones are the ionic bonds. Ionic bonds are the electrostatic attractions. And if you look at the periodic table, which all of us should always have, metals and non-metals, there is definitely a complete charge. Complete or formal charge. So if
Dr.
you look,
Lerma,
go ahead. Who's that?
can you
Salome.
push your page up a little bit?
Yes. Thank you for reminding me, Salome. And please go ahead and do remind me whenever you're not able to see it. So if you remember how many electrons sodium atom usually have, 11. If it loses 1 electron and becomes a positive charge, which means it has now 10 electrons, how many valence shell electrons are now present here? 8. Whereas in the atom, a neutral atom, there was 1 valence electron, right, in the 3s. Now it is in the 2s and 2p. So these 8 valence electrons are in the second shell. This 1 valence electron is in the third shell. Please make sure that you all remember your electronic configuration. All of you should brush up on that, how we are filling in our electrons and so on and so forth. Similarly, chlorine also has 17 valence electrons in its neutral form. When you have an excess electron, which means a negative charge is there, now you have, oh, sorry, not valence electrons, just 18 electrons. So it has a complete octet in the form of chloride. So these are your ionic bonds, and ionic bonds are very strong. The next in line are the covalent bond. But why did I show you the ionic bonds? Sometimes, just sometimes, carbon will also become a negative charge, and it can attach itself to a metal ion. Please remember this, very important. All metal ions will have a positive charge. Anything next to the metal ion or any atom next to the metal ion will have what charge? The opposite charge. What is the opposite of plus? A minus. So just sometimes our carbon can be having ionic bonds also, but depends on with which elements it is. All the metal ions will give a ionic bond kind of a feeling to carbon. The next are the covalent bonds. Now these covalent bonds arise because non-metals bond with each other. So what is the difference, primary difference between ionic and covalent? Ionic bond is between metals, non-metals. Covalent will be between non-metals. Now, before I talk to you about the different kinds of covalent bonds, which is non-polar covalent and then polar covalent, let me talk a little bit about electronegativity. Now remember, we were talking about our periodic table. And knowing the trends of your periodic table is also very important. In the second row or any row of the periodic table, the electronegativity increases. So increases from borane to fluorine. So what does that mean? Out of borane, carbon, nitrogen, oxygen, and fluorine, I'm saying that borane will have the weakest electronegativity, whereas fluorine will have the higher electronegativity. So if there was a bond between carbon and fluorine, what will we define it as? A bond between carbon and fluorine would be considered as a polar bond. Why? Because there is a electronegativity difference. The electronegativity difference means that there is an unequal sharing of electrons. So remember, what is covalent bond actually? It is just sharing of your electrons, the valence electrons. But if you look at the electronegativity values, and I'm just writing whole decimals, I'm not going to go into details. This is 3.5 and this is 4.0. You can see that there is a significant electronegativity difference between carbon and fluorine. Whenever you will have a electronegativity difference, you will say that this is a polar bond. On the other hand, if carbon was bonded to a carbon itself, do you think there will be an electronegativity difference? Is there an electronegativity difference between a carbon-carbon bond?
No.
No. And so these kind are considered as a non-polar bond. Now, the question is between carbon and hydrogen. We can understand why there is no electronegativity difference between carbon-carbon. Both of them are the same atoms. Both of them have the same electronegativity difference. Electronegativity. So the difference will be 0. But what about carbon and hydrogens? So the electronegativity difference between carbon and hydrogen is very, very negligible. If it is 2.5 for carbon, the electronegativity for hydrogen is 2.1. So it's a very, very small ratio, and we say that a carbon-hydrogen bond is a non-polar bond. So the more electronegativity difference there will be, the more polar the bond would be considered. Let's do an example. First of all, is this structure complete? It's not, because I did not draw my hydrogens. And for this class, I will be drawing this square structure, which I want to warn all of you is not the real structure. When we go to the second module, I will expect all of you to understand and know and then draw the accurate form of a carbon chain structure. But for today, let's just focus here. Why do I want us to focus here? So that you will remember that we have 4 bonds on the carbon. So I have this, and let me replace one of the hydrogens with fluorine, and then one of the hydrogens with chlorine. Okay. Now, looking at this, do you see any non-polar bonds? Ariel, is that how you say your name? Ariel or Ariel Wallace?
Ariel.
Ariel, okay.
Yeah.
So hello, Ariel.
Hi.
Did you understand this concept of polar and non-polar bonds?
I'm still trying to understand. I'm not
Okay.
sure.
Okay, I'm glad I asked you then. So polar bonds will have electronegativity difference. Non-polar bonds will have no electronegativity difference. How do you know that there is an electronegativity difference? You will look in your periodic table. As you go towards the right, the electronegativity increases. As you go from top to bottom of the periodic table, the electronegativity will decrease. So looking at this structure, Ariel, do you think there is any non-polar bond present in this structure?
Is it the carbon and Cl? I
So
mean, carbon and F.
So carbon and F, are they non-polar or polar?
Polar.
Right, they are polar. So I was asking for a non-polar bond.
Carbon and Cl.
Carbon and Cl? Is that what you said?
Yeah, I think it's nonpolar.
Now, if you look back at our periodic table, so let's see, chlorine is at the bottom of fluorine. And if I'm not wrong, chlorine is 3.0 in electronegativity. So 2.5 and 3. There's a significant difference in electronegativity between carbon and chlorine also. Do you see that?
Yeah, so there's no nonpolar.
So this bond is also polar. And the rest of the bonds, they are
carbon and hydrogen non-polar?
the carbon and hydrogen are the non-polar bonds, yes. Is there anyone who does not understand the polar and non-polar bonds? You know, in a few days, you will be looking at a structure and you will have to find out where will the reaction occur. Okay, so I will say the reaction will occur at the polar site. So you should know, am I talking about the non-polar area or am I talking about the polar area? So what does a pole indicate? A pole just indicates unequal sharing of electrons. And I think in your general chemistry, for example, if you have a HCl, the Cl, which has a formal negative charge, or a hydrogen which has a plus charge. So you either show them with formal charges or partial charges. Actually, let me write a sodium ion here. So this is a delta with a negative charge. These are known as partial charges. Why is this a negative charge? Because among hydrogen and chlorine, among these two atoms which are bonded by this bond, the chlorine is the more electronegative element. The more electronegative element pulls electrons towards itself. And this is how we show a dipole. And this is how you should always show the dipole. This is a straight arrow with a plus at the end. So this is a dipole arrow. So know this from polar, non-polar. You also need to know the strength of polar. Among these two structures, or among these two polar bonds, the CF is a polar bond, the CCl is a polar bond. And if I have to draw the dipole, fluorine will get the arrow, carbon will get the plus. When I have to draw a dipole on this bond, chlorine will get the arrow, carbon will get the plus. That is what the indication of a dipole is. The electrons from less electronegative go to the more electronegative, concentrating the number or amount of electrons more on the electronegative element, causing a pole to occur. Okay, so there is a polarization. This is negative, this is positive. There is a polarization that has occurred. And we will be using this term polarization a lot. So make sure that all of you understand polar, non-polar bonds. How do you figure out the strength? The more electronegative the element is, the more polar that bond will be. So if I have to compare a CF and a CCl, who will be more polar in nature? Elizabeth? I'm sorry, I can't read your last name. Elizabeth, chat.
It'll be CF.
The what? CF. Yes. Very good, Elizabeth. Because fluorine is a more electronegative element, you will see the strength of this polar bond will be more as compared to this. So more difference of electronegativity, more polar that bond will be. Any questions so far? Okay. Now let me very quickly show you the Lewis structure. Because knowing valence electrons from your periodic table is very important. How do I stop this? Are you all able to see my screen?
Yes.
Okay, very good. Thank you. Lewis structures. And don't worry, we will cover all of this eventually. We have covered all the periodic table, and then we covered how many bonds each of these will make and things like that. But what I wanted to show all of you were these Lewis structures. And this is how we usually make a Lewis structure. Whenever you will be given a molecular formula, you will dissect the molecular formula into its atoms. So if you look at NH3, also commonly known as ammonia, how many nitrogens do you see here? 1. How many hydrogens do you see here? 3. So I have written out these elements or atoms first. What is a molecule? A molecule is a group of atom or atoms. Okay, they can be same atom or they can be different atoms. In this case, they are different atoms. But if you think about hydrogen, H2, H2 is a group of 2 same hydrogen atoms. So when you're looking at this particular molecule, this particular example, you can look back in your periodic table again. How many valence electrons a nitrogen has? Let me show you my previous periodic table. How many valence electrons nitrogen has? 5. How many valence electrons hydrogen has? 1.
1.
Very good. So if we have to do the Lewis structure, the first thing that you need to know is that all nitrogen atoms will have 5 valence electrons. Now, why did I write it like this? I should have ideally written out the first 4 electrons in this manner and then start to pair them. Okay, so there are different rules, the off-bow exclusion principle and the filling principle. All of those are different principles. So make sure that you refresh your electronic configuration filling skills. Hydrogen has only 1. So these are all the atoms individually written out. But how do I make my molecule? When I will make my molecule, for example, I have NH3, I have to make sure whether it is a neutral molecule or if there is a net charge on it. What do I see? For NH3, there is no charge. It is a neutral molecule. So what is the total number of valence electrons I will have? There was 1 nitrogen. So 1 nitrogen has 5 electrons. And then 3 hydrogens with 1 electron each. So that is 8 valence electrons. Okay. When you start to write out your Lewis structure, always start with multivalent atom. What does that mean? Looking back at our periodic table, who can make more bonds, hydrogen or nitrogen?
Nitrogen.
Okay, thanks, Sammy. So nitrogen can make 3 bonds while hydrogen can make only 1 bond. So among hydrogen and nitrogen, who has more valency? The nitrogen. So start with the multivalent atom. I'm going to write my nitrogen out first. So the next thing that I have to remember is 1, 2, 3, 4, is that all bonds have 2 electrons between them. I do not see any other multivalent atoms. So now I can fill in my hydrogens. How do I fill those in? I will redraw my central atom. And then I'm going to write hydrogen. So I'm just consuming one of these hydrogens from here. I wrote its electron next to the nitrogen. What would this do? It is going to make a bond right here. So one bond has 2 electrons between them. And the first bond that forms between any 2 atoms is known as the sigma bond. So the single bond is the sigma bond. First sigma bond forms. And there is a probability that you can have more bonds. So when you have multiple bonds, we call them as pi bonds. Okay, can you all see what I just wrote, the pi? Okay. Black woman. Oops. Who is this black woman in charge? I'm sorry, I don't know your name.
Hi, that's me. I actually got kicked out of the Zoom, so my name went back to the default. But my name is Mia Hayet Elbasugi.
Oh, hi. Mia or Nia? N or N?
Oh, you can just call me Hayet.
Hayet? Oh, okay. Okay. Hello, Hayet.
Hi.
I just wanted to touch base with you. Are you here? Could you see what I just drew? A pi bond. Could you understand what is the difference between a sigma and a pi bond?
Yeah, so I know you're talking about how the bonds are formed.
Mm-hmm.
So, is a pi bond like a single bond and the sigma is like a double bond?
No. The sigma bond is the single bond. And when you will have multiple bonds, like the double bond, the triple bond, that is when you will start to have your pi bonds. But very good, Hayat. I see that you're on track. Anybody else has any questions or doubts about what is a sigma bond and what is a pi bond? Okay, very good. Thank you, Hayat. Yes, go ahead.
Yeah, thank you. One thing is just like it's really hard to read your writing.
Handwriting.
But yeah, it's not because of the font or anything. It's just because of maybe my service. It makes it really blurry.
Mm-hmm.
Can you upload like pictures of your notes to Brightspace?
Actually, that's a very good idea. I will keep that in mind. And I'll number my notes. That's a very good idea. Thank you, Hat. I will keep that in. And if I forget, please remind me.
For sure. Thank you.
Okay, very good. All right, so once you have figured out that you need a single bonds for sigma bonds, after all the single bonds have been placed, then you will add the lone pair to complete the octet. Okay, this is the time that you can place or keep your lone pairs. Okay, so multiple bonds can be used if you run out of electrons. And what does that mean? I'll show this to you on your next example that we are going to see. But always check back. That the information that you had in the beginning matches with the information that you were given. So if you look at the 3 hydrogens, so I used up this, I used up this, I used up this. And each of these, so this makes a bond right here, this makes a bond right here, this makes a bond right here. What is left is the lone pair. And that is completely legitimate, completely reasonable structure or Lewis structure of ammonia. Okay, let's do another example. Oh, let me keep the sequence sheet here. This is from your skill builder. So your book, David Klein, has skill builders. Please make sure that all of you are completing those skill builders also. So let's try with CH4 oxygen. So if I compare it with my notes, which I have, what is the first thing that I must look at? Is this a neutral molecule or there is a net charge on it? It is a neutral element. What is the total valence electrons that I see on it? So there is 1 carbon, and carbon has how many valence electrons? 4. And then I have 4 hydrogens. Each hydrogen has how many valence electrons? 1. And then I have oxygen. 1 oxygen.
6.
6 valence electrons. Very good. And so 4 plus 4, 8 plus 6, 14, right? Yeah. So this particular structure in all, overall, should have 14 valence electrons. So I have to start with my multivalent atom. Among carbon, hydrogen, and oxygen, who is the most multivalent? Going back to my periodic table. How many bonds carbon can make? 4. How many bonds oxygen can make? 2. How many bonds hydrogen can make? Only 1. So I will first write out my carbon. And I will draw all the 4 valence electrons around it. Before I fill in my hydrogens, I will fill in the next most multivalent atom, which is oxygen. Now, how do I know that I have to place carbon and oxygen next to each other? I could have this separately, right? So this is the time that I'm going to do my trial and error. This is not my final molecule or final structure. I'm just going to look or place it around it. So oxygen has 6 valence electrons. Now I have 4 hydrogens that I have to fill in around. Can anyone suggest where all the hydrogens can go in? Can a hydrogen be placed between a carbon and oxygen?
No.
How about the rest of us?
No.
Now, because hydrogen makes only 1 bond, we cannot place it between the two atoms, we have to place it outside. So one right here, one right here, one right here, and one right here. So hydrogens can be considered as fillers. Okay, you don't have to fill them in at the beginning, but you will have to fill them in eventually. So we started with the multivalent atoms. We have placed all our single bonds. All our electrons have been accounted for. Now we will keep our lone pairs. So I'm going to redraw the structure again in my square format. If you look back here, if you check back, carbon is making 4 bonds. Oxygen is making its 2 bonds. Hydrogens all over are making their 1 bond. What I did not write is O with its both lone pairs. I can write oxygen with lone pairs like this. I can write oxygen with lone pairs like this. I can also write oxygen with lone pairs like this. I'm not sure how your general chemistry class went, but I get a little bit confused with the negative charge. It is completely fine. But when you're doing organic chemistry, I will assume that you're writing a formal charge here. Okay, a formal or a complete charge. So please avoid writing anything like this. Both of these are acceptable manner of you writing the lone pairs. Okay. Now it is almost 2 o'clock and let's do a little exercise. All of you have your paper and pen. CH3, CH, okay, actually. Okay, I want you to write the valence electrons in structure A and in structure B. So this is CH3Cl and this is C3H8O. I'll give you the next 3 minutes. To solve it on your own, and then I'll call out some of you. Have said that it will have 14 valence electrons, and that is the correct answer. Very good. Anybody who could not figure this out? Okay, good job. Very good job. So this carbon and this chlorine, carbon has 4, hydrogens have 1, and then 6. From your chlorine. If you look at C3H8 oxygen, what is the valence electrons for C3H8? For C3H8 oxygen,
20.
It's not 20.
Just a second. 3, 6, 3, 4, 12. 12 plus 8, 20. Yes.
So oxygen has 6.
With oxygen, okay. With oxygen is 26.
Yes. So H8 will give you 8. And then 3 times 4 is a 12. Okay, I'm sorry. I had put a repeat here. So this will have 26. And this will have 12. So I didn't want you to spend time on calculating this, but I want all of you to try and do a Lewis structure, a Lewis dot structure for this particular compound, CH2 with the oxygen.
12.
Yes, very good.
Okay.
But I want you to make the Lewis dot structure for this. And I will point out to anyone and I will call out your name and you will have to show me your paper. If you're done with the Lewis dot structure of this, you can go ahead and do the Lewis dot or any structure for this. You don't have to be, it does not have to be Lewis structure. For B, you can draw any structure you would like the bond shape one. So this is the dot Lewis structure example. And I want you to do the Lewis dot structure example for this molecule also. Just to help you a little bit, I'm going to keep this note here on how to figure out your Lewis structure. If you're given the molecular formula, how will you figure out the Lewis structure? Nelson Brown.
Hold on, I gotta set up my camera.
Oh, don't worry, I'm not asking you for the answer yet. I was just
Okay.
checking on you. Are you doing okay?
Yeah,
Do
I've
you
got
need
it.
any help figuring out? Or you're
No,
there,
I've got
almost there. Okay, okay, good, good. So Nelson, are you ready now?
Yes.
Okay, you can go ahead and share your screen and I'm going to put you on spotlight.
Can you see? Hold on. Let me unturn.
I can see. Can everybody else also see Nelson's work? Very good, Nelson. Very good. I'm very impressed. And that is the right way to do it. Very good. Very good. Thank you so much. And so,
I have a question.
go ahead, go ahead.
Well, I tried to draw out B, and
Mhm.
I did a 3-carbon chain and 8 hydrogens surrounding it on like top, bottom, and on the sides. Where will my oxygen be attached to hydrogen as well?
So remember, a hydrogen cannot be placed between a carbon and oxygen.
Right. So I would just put the oxygen on top of one of the carbons and then put.
Yes, you can replace one of the hydrogens
Okay.
Like carbon has 4 bonds with hydrogens. You start replacing one of them by at a one time.
Okay. Thank you.
Okay, very good. And coming back to this, I just wanted to remind you that you will draw your multivalent atom first, then the next multivalent atom, and then you will draw your other hydrogens. Now the problem here is we have run out of electrons. What about these two guys? This is the time that we will introduce our pi electron, the multiple bonds. And so I will make a pi bond here. So I'm going to redraw this. This is my sigma bond, the first bond that forms between carbon and oxygen or any two atoms. I will draw another bond also. The second bond that will form is my pi bond. And I will definitely have the two lone pairs right here.
Dr. Verma,
Yes.
can you push it down some? I'm sorry.
Yes. No, you're fine. You're fine. And so the other two hydrogens, I'm going to make them like this. Any questions on this? So I have introduced my multiple bonds right here. First bond between two atoms will be the sigma bond. The second bond that forms between two atoms is the pi bond. Now I can make this from here, or I could have made this structure also. Why did I give a negative charge to oxygen? Because of the polarity. Because of the polarity and because oxygen is electronegative, I will give the negative charge. The oxygen will carry the negative charge and carbon will carry the positive charge. How many bonds carbon is making? 3. How many bonds oxygen is making? 1. Both of them are not completely satisfying their number of bonds that they can make. So remember we were talking about this. Carbon makes 4 bonds, oxygen makes 2 bonds. And here, 1 bond is less from both of them. And so, is this a reasonable Lewis structure? Reasonable dot Lewis structure of this particular molecular formula? Yes, it is. If we compare these two structures, structure A and structure B, definitely structure B is more stable. But A is also a reasonable structure. What about if I had, by chance, given the carbon a negative and oxygen a positive? Did you see what I made here? 1 electron. One of the electrons is lost. Whenever you will have a positive charge, electrons have been lost. But what about this carbon? It means that I have negative charge or 5 valence electrons on carbon. Are 5 valence electrons on carbon even possible? No.
No.
And so this structure will not be possible. Because if you give a negative charge on this carbon will not have 4, but 5 valence electrons. 1, 2, 3, 4, 5. So this molecule or this structure will not be allowed. Any questions so far? Now the next part that I wanted to start today is known as the constitutional isomers. And during this course, we will be doing a lot of other isomers also. These are the most basic ones. Okay. I will also show you a sequence sheet, which is posted on your lecture slides. I'm sorry, not on lecture slides, on your Brightspace course, where you can figure out how to look and form constitutional isomers. But what are constitutional isomers? They have same molecular formula, but different connectivity. What does that mean? If I look back at my C3H8O, I have 3 carbons. The most multivalent I will arrange first, followed by my next multivalent, which is oxygen. And then I'm going to fill in my hydrogens. Now what I'm showing you right here is one of the most basic forms of chemical structures. As we progress through this course, we will be seeing more complexities also. But if you look at this structure, I always will cross check 8 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 3 carbons, 1 oxygen. Always check back your work. So I can either arrange them like this, or I can place my oxygen between 2 carbons. Any questions what I did? So carbon is going to make 4 bonds. I did not tell you what are these, so I'm going to fill in those as hydrogens. This carbon will also have its 4 bonds. This oxygen can make only 2 bonds. It is doing so. So I don't need to fill in any other hydrogens here. Is the molecular formula exactly the same? Yes. But is the connectivity exactly the same? No. So this structure C and this structure D, even though they have same molecular formula, they have different connectivity. And hence we call them as constitutional isomers or connecting isomers. Now I want to remind you about this structure. How many bonds this carbon is making? 1, 2,
4.
3, 4. Very good. Yes, 4. So remember, always check back your work. So the different arrangements is what are causing the constitutional isomers to form. So we just talked about a little bit about resonance structures. If you look on the slide 13, I have also shown you separation of charges here. Okay, we will look at resonance structures in more details when we go to module 3. But Lewis structures are not sufficient. Okay, there are possibility of forming more than one structure for the same compound. They are different from constitutional isomers. Why? Because the connectivity is exactly the same, but the location of electrons is different. That is what differentiates a constitutional isomer and resonance structure. Okay. The last thing that we will look at today is the hydrogen deficiency index. Now, this is in your chapter 14. I think it's 14.16, if I'm not wrong. But it is included in this part of module because it is very important for all of you to understand that how degree of unsaturation can help you draw a reasonable framework of your chemical structure. Okay, so this is on slide 5. And so HDI, hydrogen deficiency index, or IHD, index of hydrogen deficiency, or unsaturation. All of these terms mean the same thing. If you're given a molecular structure, how will you figure out this? Now, let's say that ideally, these are the structures that we have been dealing with, right? All of them have single bonds, except for one, I think we just did, where there was a multiple bond, where there was a double bond. The rest of them had only single bonds, right? So these structures have maximum hydrogens that carbons can contain. So for example, if you have C4, these are the maximum number of hydrogens that 4 carbons can contain. So there is this molecular formula or for hydrocarbons. What are hydrocarbons? The carbon hydrogen chains. So Cn plus H, 2n plus 2. What is N? The number of carbons. So let's fill this in. If there are 3 hydrogens, how many hydrogens should be there? 2 times 3?
8.
Okay, very good. So C3H8, very good. So if you count here, we have 8 hydrogens. What about this? C4. 2
10.
times 4, very good. C4H10. And if you count, these are the maximum number of hydrogens a molecule can have. And so we call these as saturated molecules or saturated compounds or saturated hydrocarbons. So what is an unsaturated hydrocarbon? Let's just look at this structure. What if I remove these 2 hydrogens? Oops. So I've removed these 2 hydrogens. How many bonds this carbon is making? 1, 2, 3. What about this carbon? 1, 2, 3. So if I remove 2 hydrogens, I have introduced unsaturation. How is this relatable? The degree of unsaturation in the carbon chain indicates what is the number of hydrogens that is missing. So for example, 2 hydrogens are now missing, which will equal 1 degree of unsaturation. So if you're given the molecular structure and you look at the structure, and it could be anything. This is a chlorine that I've placed here. How many pi electron or pi bonds do you see? So this is what the unsaturation will tell you. Pi bonds or rings. How many pi bonds do you see? This is the sigma bond and this is your pi bond. And hence you have 1 degree of unsaturation. If you have a structure, carbon, 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 and I have 2 pi bonds. Now, how many pi bonds do I have?
2.
2. And that is the degree of unsaturation. 1 pi bond, second pi bond. What about here? How many pi bonds do I have in this example? Still 2.
2.
In a triple bond, the first bond that forms is the sigma bond. The second bond that forms is also a pi bond. The third bond that forms is also a pi bond. So whenever multiple bonds are forming, you will count their pi electrons. Let's do one more. Do you think that having halogens will cause any unsaturation? Dehazia? Dehazia Hopkins?
Dehasia.
Dehasia. Okay. Dehasia, do you think if we replace a hydrogen with a fluorine or a chlorine, will that affect the degree of unsaturation? For example, I had a halogen here also, but did I look at this when I was looking at my degree of unsaturation, or I just looked at the pi?
You just looked at the pi bonds that were formed?
Yes, yes. And so even in this particular structure, I don't see any pi bonds. But what do I see? I see a ring. So this one ring is the degree of unsaturation. So please be careful. If you're choosing the hydrogens, you will then divide it by 2. But if you're looking at the number of pi bonds or the number of rings, then that will equal to your HDI.